Hello everyone, this is Dibjyoti here. Today we are going to talk about one uh, problem on counting unique number of paths in a 2D maze. So this problem is from LeetCode and we'll try to solve it in an efficient manner. So let's quickly go to the problem statement. So I'll share my screen. Uh, So let me just start the slideshow. So we want to find the unique number of paths in a maze. So what does that mean? So if we go into the problem statement, mainly what we are concerned about is that there is a robot and the robot is trying to go trying to travel through a maze or a grid, and we can consider that initially the robot is located at the top left corner, uh, and then the robot tries to go to the bottom left corner, and the only way the robot can travel is it can either move down or it can move right. So this is a very important constraint, that the robot can only move down or it can only move right. So if you are not getting the I thought you're not getting the problem on not being able to visualize it, we will be describing giving a visual description of this in the next slide. So basically now what we are saying is that there's a m cross n grid, and we'll be given this m cross n, this m and n, and all we have to do is that we have to figure out what are the total number of unique ways in which we can traverse from this 0 comma 0 grid, that means the top leftmost corner cell, to the right and the right and bottommost corner of the cell, and so what are the unique number of paths. So let's take a visual example. So we can see that this is kind of the grid, and the robot is at the start, which is the top leftmost corner, and then the finish is at the rightmost and the bottommost corner. So basically the robot can only move in the right direction or it can move in the downward direction. These are the constraints that are given to us. There are some more constraints that we are going to discuss, but this is the problem setting and we have to count it. So basically, we are mainly concerned. So if you look at this finish cell, we want to figure out how many ways the robot, how many unique ways the robot can travel from that start to that finish. So if we have understood this, then you will be able to figure out that there is no way that the robot can move up or it can move left. So any leftward or upward movement is basically prohibited. So this the movement that is shown in this slide is not a valid move. Whereas the robot can move down or it can move right. So this is the valid move. The arrow position talks about the valid move. This is a valid move and the robot can take either of these. Now, so what are the constraints of this? So the constraints of this problem is that the m and n, that is the integers, or that guides the size of the maze or the grid, is varies from 1 to 100. That means, so when it varies from 1 to 100, that means we are guaranteed that there will be at least one cell, and at most there can be 10,000 cells, because m and n can be 100, so 100 cross 100, there can be 10,000 cells. And we are also given that uh, the number of unique answers will always be less than 2 to the power 109. That means it will not overflow a end. So that's what we are given. These are two things that we are given to better code this problem. So again, just to recap, we are looking at a grid, and a robot is sitting at the top leftmost corner of that grid, and it is trying to traverse to the bottom and rightmost corner, the one that is marked with finish. And at each step, the robot can only move either to its right or to the down. So if you look at the cell marked with uh, blue, if the robot is there, it can either move down. If the robot is here, it can move right. or it can move down from here. So at any point, the robot can only move right or it can move down. So that is the constraint that is given to us. And these are the additional constraint that we should understand so that we can code this up. So let's take an example and see how this works. So suppose the input was given m equal to 3 and n equal to 2. With 3 basically number of rows and n 2 number of columns, how many ways we can do that? So if you can draw on your board and you'll be able to see that there are 3 basic ways in which you can do that. So if you have a 3x2 board, so if you go here, a 3x2 board will be, so there is 3 and there is 2, right? So there will be only, so this part will not be there, only there will be first two columns will be there. So if the robot is trying to go in this from this to this, so then the finish will be this and the start will be this. So this you can ignore from here if you're just looking at a 3x2. So 3 is the number of rows and 2 is the number of columns. So if the robot starts here, it can you can see that it can either move from here to here, then here, then here, or it can move to here, then here, or it can move from here to here. So there are only 3 unique paths. So that's why the answer in this example will be 3. So if we look at it, so if we just restrict for the first 2 columns and the 3 rows, then we know that either we can go right, down, and down. So that means right and then down and down, or we can go down, down, and right. That means we can go down, and then right. Or what we can do is that we can go down, right, and down. That means we can go down, then right, and then down. So these are the 3 ways we can do that. So this is the simplest example that we can take for or a grid of size 3x2. So for a 3x2, we are looking at the grid. So first, these are the 3 rows, and the first 2 columns we are just looking at. And if the robot is there, the finish will be here. So as the example says that we can either move down and then right, or right, then down and down. So these are the 2 unique paths. And then there is one more unique path. You move down and then you move right and then you move down. So these are 3 unique paths that is possible. The robot cannot move in the diagonal fashion, so it will not be able to. So this is not a valid path. So so the only valid path is if you go the right, then down and down, or if you go down, down and then right, or if you go down and then right and then down. So these are the 3 unique paths. So for now we will be given an arbitrary m and n, and we have to figure it out. So we can see that for a 3x2 case, or 3 m equal to 3 and n equal to 2 case, it is not that difficult to figure out. Now, let's talk about what are the base case. So whenever we are trying to solve a program or we are trying to write a code, we want to be very aware of what is the base case to start with. So the base case here is that if there is only one cell, that means there is only one cell. If we go back to this maze, and suppose the only start was there, so both start and finish are the same thing. So then how many ways the robot can reach from start to finish? And we know that the answer to that is 1, because there is only one unique path, right? So if there is only one cell, there is only the number of ways is 1. So if we are looking at all these cells which doesn't have any cell before that or above that, so this cell has no cells to the left of it or to the above it. So the number of ways to if this is the only cell present will be 1. So this gives us a way to initialize, because we have to initialize the topmost and the leftmost cell. So we'll come to that, but this base case will help us to initialize. Also, the minimum value of m and n can be 1. So so if there is no kind of cell in the maze, then there is no way you can traverse. So but here we are given m equal to 1 and n equal to 1 as the minimum count. So in that case, the minimum answer will be always 1. So this is a base case that we should be aware of to solve this problem. Now, let's look at some interesting observation that we can use to solve this problem, right? So one of the interesting observation is that if you look at this maze or this grid, and the robot is sitting at the top leftmost corner, and if you look at the first row of this grid, what we can see is that so there is only one path in the top in the top row. Topmost row has only one path, because there is no cell above this. Hence, there is no way to that a robot can come down to this cell. The only way a cell can reach this or this is from the left hand side, and hence there is only one path, right? So that is the first important observation that we should have, that there is only one path to reach any cell in the first row. So any cell in the first row will have only one way in which or only have one unique path. Similarly, any column, like any cell in the first column will also have only one path because there is no cell in the left part of it. So there is no way to reach it from the right by a right movement. The robot can only reach any of this cell by a downward movement, and hence the only way a robot can reach is via down movement, and hence the number of unique ways to reach any of this cell in the first column is one. So what we observed is that the number of ways to reach the first row or to any cell in the first row, the number of unique ways to reach any cell in the first row, and the number of unique ways to reach any column in the any cell in the first column is always one, right? So there is only one way to go to any cell in the first row, and there is only one way to go to any cell in the first column. And this will again help us to figure out our base case, right? And now we want to do an interesting observation. So suppose we want to find what is the number of ways in which we can reach this path 1, 1, that is where m equal to 1 and n equal to 1. So how many ways we can reach it? And if we know that the number of so in the how many, I mean, the way we can reach into this cell is either we have come down from this the above cell, or we have come to the from the left side of the cell. And since the number of so what we can say is the number of ways to reach this particular cell is the sum of the number of ways to reach the cell above it and the number of ways to reach that cell from the left side, right? So if we know these two, then we can actually compute it for any arbitrary cell. For any inner cell, we can compute it. So if this is not clear, so suppose like we have two in this maze we have two cell. So we have this cell called I comma j, and we want to reach that cell. So the only way we can reach this cell is that from I minus 1 comma j, we can come down, or from I comma j minus 1, we can go to the right? So these are the only two ways we can reach it. So, and this has been shown in this image that we can only reach I comma j either from I minus 1 comma j or from I comma j minus 1. So the only ways. So if we know, so for any particular cell, if you want to know that how many unique path is there for I comma j, then we can figure it out if we know the number of unique path of to reach I minus 1 comma j and the number of ways unique path to reach I comma j minus 1. If we know these two parts, we can easily compute the number of unique paths to I comma j. And this is something, and this looks like a recursion, right? So we have we have found a recursive relation that for any ij we can do that. And if we do it for any ij, the only thing that we have to compute is what is the value for m minus 1 and n minus 1, a grid of m cross n size. The leftmost and the bottommost cell will have a coordinate of m minus 1 and n minus 1 because we are starting from 0, right? So since it is a zero-based index, so we can only the leftmost and the bottommost cell, or the rightmost and the bottommost cell, the finished cell will have an index of m minus 1 and n minus 1. And if we can compute it for any ij, we can also compute it for m minus 1 and n minus 1, and hence we'll be able to compute. So we will start from here, and then we'll compute in this fashion by looking at the top cell and the left side cell, and we'll compute it in a recursive fashion, and we can easily compute it for any m cross n for any board that is given to us. So this is the first solution that we are looking at, and let's look at the code, how it looks like, and then try to see how the solution will be. So if you look at the code, this is very simple, right? So our base case is that if either the row is 1, that means m is equal to 1, that means it is the first row, or it is the first column. So what we saw is that if it is the first row or if it is the first column, then there is only one unique base. So if it is equal to if the robot is in the first column or in the first cell, you can just return the number of unique path is 1. But if it is not in the first column or the first cell, then what we can do, we can look at the cell just above the particular cell or the cell just the left of that particular cell, and we can sum them up. And then this is the recursive solution. And this is very simple, right? So it's just 2 lines of code to solve this entire problem, and this works fine. But the only problem here is that we have to figure out what is the time and the space complexity. So in this kind of a solution, in this kind of a recursive solution, the time and space complexity is exponential. So why it is exponential? Because we are calling. So we will see why this is exponential. But so we have to be careful while doing this recursive call, because recursive call might have duplicates in the path, and we will see that we are actually doing duplicate computation for which the time complexity is going to exponentials for very small. So we are trying to calculate for any so here n means the number of cells. So if the number, so as you can understand that we have to calculate for a cell equal to 10,000. So 10,000 can be the max number of cells that can happen. So this is going to be a pretty large number if you are going to compute it, and hence we'll not be able to solve the problem using this because we'll run out of time because of the exponential nature of this problem. So why this is exponential, right? So and we feel like that when we are trying to see why it is exponential, but there is a very simple reason. And if we just look at the recursion tree for this problem, we'll be able to figure out. So what is a recursion tree? Recursion tree is the computation tree, how the recursive call happens. So if you look at the way the recursive call happens, it's actually a tree-like structure. And if you look at this, we will figure out why the duplicates are happening. And so if we look at this, so if you look at so suppose like we are trying to compute it for I plus 1 comma j. So this is the cell that we're trying to compute it for. So for I plus 1 comma j, we have to either go to the row just before it. So the row just before it has so if this is the particular cell that we are interested in, so the cell that is just one row before this, that means just on the above this particular cell is I comma j, and the one that is just to the left of it is I plus 1 comma j minus 1. So you can just figure it out. So if we do if we do the row minus 1, so I plus 1 minus 1 will be I, and then j will remain fixed. And for this, we have the I plus 1 fixed, but we have to decrement j because we are going to the left. So so as you can see that for both of these paths, we have to compute the same value I comma j minus 1. So similarly, if you look at the entire recursion tree, there will be lots of values which will be computed multiple times, and this is causing the problem of exponential time complexity. So the question here is that how can we solve it, right? So we are seeing that there is a problem of duplicate computation, and duplicate computation will always lead to higher time and space complexity. The way to solve any duplicate the computation is by, if you can store, if you know that something needs to be computed multiple times, if we have computed once, you can just store it. And this is where the memoization concept comes into handy. So in dynamic programming, we have this concept of memoization, so which helps in storing this. So this problem has all the ingredients of a dynamic programming. So it has optimal substructure, because if and it also has this sub problems. If we solve this sub problems, then we can easily solve this, right? And that is the kind of solution that we are looking at, is that we are trying to look at a problem which has this optimal substructure, and using this optimal substructure, we can easily solve this problem once we are being able to memoize this. Once we can remove this duplicate computation, then we can easily solve this problem, right? So how are we going to solve this problem? So suppose we had, so instead of calling this recursion multiple times, suppose we had an array of size in D be the array of size m cross n. So why we are taking a size of m cross n? Because we know that the grid has m cross m into n cells. So we will be we'll take a array of size m comma n. That means there will be m cross n number of values in that array. And how we will compute this array? So we can say that each cell of this array is dedicated to each of the cell in the particular grid. So for a particular say, column and a particular row, we can just compute we can use the recursive formula. So we can say that the column or row value of D, which stores the number of unique paths, is nothing but is sum of the value just above that particular row. So the one where from the robot can come down, and the one is on the from the robot can also move right from the left cell. So one is the count number of unique paths of the left cell. So one is on the number of unique paths from the left cell, and the other is the number of unique paths from the top cell. And with this, if we sum them up, then we get this number of total unique path for a particular column and row. So if we know this, then if we can store this, then we don't have to compute it multiple times. And since we will be so what we will do, so this is the final code of how to solve this problem. So what we can do is that we can initialize the entire array with 1. Why we are initializing with 1? Because we know that if there is only one cell, there is only one unique path. So we know that base case, hence we are initializing every cell with 1. That means if that cell is present, then the number of ways to unique path from start to finish, if that only cell was present, is 1. So we know this base case, and hence we are initializing everything. And now we are going from the column, and then we are traveling from the row. So for each of the column we are going, and we are summing it up. For each of the column we are and then for each of the row we are going and traveling and figuring out. For each column and for each row, what we are trying to do is we are trying to fill this array using the recursion relation that we have. And at any point, what we are just trying to do is that we are sitting at any I comma j in a cell, and we are computing it based on the value at I minus 1 comma j and I comma j minus 1. So I minus 1 comma j is the cell just in the row before from which the robot has traversed down, or it is from the cell which is on just one column before, from which the robot can traverse to the right. And these are the only two possible ways to reach this. So the number of unique paths will be the sum of these two. So with this solution, we can actually bring down the time and space complexity to the order of m cross n, where m cross n is the size of the array that is given. So the 2D array size that are given, so it will be so capital N and capital N denotes the maximum size of m cross n that can happen, and that is the order of complexity that we have. So for any given m and n, our complexity will be m into n, and the auxiliary space that will be required here is also m comma n, because of the store entire thing on a 2D table. So this is the time and space complexity, and we know that this is linear in terms of the number of cells in the grid. The recursion tree was exponential in the number of cells in the grid, but this is kind of linear, and hence this is a much better solution to the solution that we saw. So we have to traverse any cell in that grid. We have to traverse at least once to figure it out. So this is the dynamic programming solution, and this is the optimal solution. So for this problem. So thank you for listening to this tutorial, and hopefully you have enjoyed it. Please reach out for any questions.